whole battle with my computer this morning, was not acting appropriately, which gives me cause for concern given I already had one reset at one point this year, which don't want to have to ever do again. All right, so talking about regressions today. So when we talk about linear regression, it's a straight line relationship between two quantitative variables. So again, that regression line is going to be kind of the closest possible line to all the data points in our data set. The way we actually do that is one way you can possibly do that is like you build like a square for each data point where it's the distance to the line, and then you make like a square that has that same side length. And you do that for every data point, and you try to move the line around so that it minimizes the total area of all the squares. I think that's the way the calculator does it, is with a least squares line regression. But there's different techniques to do this. All right. So what is the point of this regression? It's used to make predictions. So if this regression line approximates this data set, we could use that then to predict, like, how much is the car worth after driving it 80,000 miles or something. Everybody's okay with that idea? Okay. Oh, yeah, there you go. Least squares regression line. All right. So let's talk about how to, what this regression line really means. Again, this is like a model for the data. So the y equals mx plus b, since it's linear regression we're talking about. That's like the equation for a line. We use the y hat here. That'll be like the predicted value. That's like a future value. M is like the slope, which is basically describing how much change you have in your y variable per 1 unit change in x. And then the b is the y-intercept. That's like the predicted value of y when x is 0. So if we go back to this equation, or this model or example here, let's say the slope is just like -2. Okay? What that would mean is like the value of the car decreases $2 per every 1 mile the car is driven, is basically kind of what that would be saying. So again, you want to describe the slope in terms of like your y and x variables. Everybody okay with that? And then this value here at like, I don't know, $38,000 or something is the value of the car at time 0, or after 0 miles have been driven. It's basically the value of the brand new car. Everybody's okay? That's a question I'll ask on the test, is why I'm making a big deal of it, to describe what the slope and y-intercept means in terms of the variables. Easy question, but like, you don't see it modeled. It's like, what do you want me to do with this? All right. Okay. So when we talk about making that our least squared line, one of the things that we need to do is calculate a residual. And that's just the difference between the observed value and the regression line. So that's that distance in the y between a data point and the regression line. That's what we mean by a residual. It's that vertical distance. Remember when we talked about it just a second ago? That's what we mean. So again, that's just our observed y, so the y from the data point, minus the predicted y, that's the y from the regression line. So here's an illustration of these residuals. Everybody's okay? Using the same picture from before. So again, what you do is you end up trying to minimize these residuals when we create that best fit line. You won't ever have to do that by hand. The calculator will do that for you, but that's what's going on in the guts. All right, let's take a look at this example here. So a scatter plot with the regression line shown below represents the relationship between the average number of points scored per game and the number of wins for 12 college football teams in the SEC. You can tell this is an old slide because there's more than 12 teams in the SEC now, right? I think. I don't know. I don't really follow college football, but it feels like all these conferences have way more teams than they used to. All right. So the equation for the regression line we got from plotting our data is this. Can somebody tell me what the slope means in context of the variables? So not quite. So remember, it's going to be y over x, or y per x. So the y is wins. So I would say a team would win 0.437 more game per one additional point scored, or average point scored.
So 1.437 of it.
Yep. Because the y is wins, right? So you'd expect your win total increase by 0.437 as your average point score increases by 1. Does that make sense as to kind of how to phrase that? Again, it's just, you're basically just using the slope, and it's, change in y over change in x, right? So it's just, slope per y, or slope change y per change in x. So we'd say like we increase because it's positive. Okay. How about the y-intercept? What would you say that means? Okay, what does that, but in context? So again, this is a y value, right? So is it talking about wins or points? Wins. So you'd expect a team to win negative 3.75 games if they score how many points on average? Not 1. What is the x coordinate when you're on the y-axis? So like a y-intercept, right? The x value is 0, right? For all y-intercepts.
Oh, yeah.
So you'd say that a team that scores like 0 points per game would expect to win negative 3.75 games. Does that make a lot of sense in context? No, right? You can't win negative games. But you expect a team that scores no points to be pretty darn bad, right? Hard to win any games that way. I mean, you could get some ties, I guess. All right. Does that feel okay? That's the kind of how to do that description. You'll get some practice here in a little bit, doing the same thing. All right. So it says calculate and interpret the residual for South Carolina, who scored 30.1 points per game and had 11 wins. So I'm going to compare that 11 wins to the output of this equation when I plug in the 30.1. Everybody's okay with that? I'm just going to look at the difference. So when I plug in the 30.1, I had 9.4 wins predicted. I actually won 11 games. So the residual, the difference between the actual and the predicted was 1.6 wins. Everybody okay with that? Sports fans, what might account for this? That a team's winning more games than predicted based on the points scored.
Individual players or bad teams.
So it could be strength of schedule, right? If you play a lot of lousy teams, maybe you don't have to score that many points to win. Sure, that could be. What else?
Then overtime.
Yeah, defense, right? Like if you have a very good defense, maybe you don't need to score that many points to still win, right? So like things like, if you're asked to explain in context, those would be good reasons to like, oh, why is this, prediction not quite, didn't do a great job in this case. Or you could just say things like, luck, you won some games that you shouldn't have because the other team, did something silly at the end of the game where they had it, they should have beat you and they committed a penalty and got the point, their touchdown called back, or, their best player was injured or something. Like, can't discount luck. All right. So, again, we talked about this idea of a least squares regression line. So the idea here is that we place a perspective best fit line in here. We calculate the residuals. We use those residuals to make like a little square. And the idea is we want to move that regression line around so that the area of the squares, the total area of the squares, of all squares, is minimized. So in general, what that means is that the best fit line is as close as possible to all the data points, or to the set of data points. But that's the idea. The calculator will do all of that for us. We're not going to do any of that by hand. That's actually kind of a complicated optimization problem. Now, we can calculate the slope and y-intercept by hand without doing any kind of optimization here. So, to calculate the slope, for that best fit line, we can take our R value, our Pearson product moment correlation coefficient, that R value that we know how to calculate, and multiply it by the ratio of standard deviation of y divided by standard deviation of x. That'll give us the slope. And we can calculate the y-intercept by doing the y-average minus the slope times the x-average. So these are just two formulas that allow us to calculate the equation of this best fit line without actually having to solve the optimization problem. This is actually the result when you solve the optimization problem, is you get this formula to fall out of it. We're not going to solve that problem in class. It's beyond the scope of what would be required even for like an AP calculus course. You wouldn't be doing this. It's actually a fairly difficult thing to do, but a computer is very good at it. All right, feel okay? So these are just the formulas. All right, let's circle back and look at this again. So we have this regression line shown. Price is equal to negative 0.1629 times the miles driven plus 38,257. Again, we can see the X is miles driven and the Y is price in dollars. Wants to take a stab at interpreting what the slope means in context of the problem.
So it would be decreased by -0.1629 for every mile driven.
Okay, negative 1.629 watts. What's the unit? dollars. So basically you lose 16 cents for every mile you drive your car, is what this is saying. Does that feel okay? What about the y-intercept?
As you increase by 3,257 price just decreases.
Remember,
It's gonna be from 0, right?
the y-intercept is always when the x is 0. So if you've driven 0 miles, the price of the car is
Okay.
38,257.
Right.
So the y-intercept is always if you've done 0x, this is the y, right? So it'll always be that kind of format. So again, we predict to go down by 16 cents for every mile that we drive, and that's the value of the truck when it's been driven 0 miles. Basically the sticker price. All right, so the value of these linear models, these regression equations, is that we can use them to make predictions, right? So like I could use this to predict the value of a truck that's been driven 100,000 miles. So I can plug 100,000 miles into this and see what it pumps out. So $21,967. Everybody's okay there? So that's called making a prediction, right? None of my data points was actually for 100,000. I'm just predicting how much I think that truck should be worth based on the data we've collected.
If
Now-
there is one with the data points,
Well, it says if it asks for a prediction, you're going to always be using the best fit line. So 2 things we have to be careful about, though. If you're making a prediction, 2 ways your prediction can go wrong. Or 2 things we need to check to make sure the prediction's going to be any good. Let me say it that way. That's probably the better way of saying it. So 1 is you want to stay away from doing extrapolation. So if I go back here and I asked you to predict the value of a truck that's been driven 500,000 miles, notice what's the biggest data point here? It's like for 140. How much do you think a truck that's been driven 500,000 miles is going to be worth? Yeah, basically 0, right? Not much. You know, $250 for scrap or whatever. If I draw this out, what do you think the value is going to actually be, though, if I plug $500,000 into this? Probably going to be negative, right? Does that make any kind of sense at all to have negative value car? No. So you want to stay away from extrapolation. Really what you want to be doing is what's called interpolation, which means you want to pick or you can use your model to make predictions between your smallest x in your data set and your biggest x in your data set, but you don't want to go outside of that. So as long as you're doing interpolation, ideally your model does a pretty good job of predicting, assuming that your model's a decent fit. So the second piece that you have to worry about is how good of a fit is your model to the data. Now we have a number that describes this for us, right? What is the number that describes this for us? It's the value for R. It's your PMCC. So if your R value is lousy, it means that your model isn't a good representative of the data. So even if you're doing interpolation, you're probably still going to get a bad prediction because your model just doesn't fit very well your data. So those are the 2 things you need to check before you make a prediction to decide if this prediction is even going to have any value at all. Right? So does your model fit your data? Is the R, pretty good? And then, are you doing interpolation or extrapolation? Extrapolation is pretty unreliable. That's how you end up predicting that, like, the average temperature on Earth is going to be like 10,000 degrees in 100,000 years, because you're using extrapolation for your weather model, or make a prediction using a weather model that's like, it's probably not valid. It's too far out. You get ridiculous things coming out when you extrapolate too far. And I would say in general for extrapolation, the further you are away from to the limits of your data set, the worse prediction that is. So if I wanted to predict at like 150, that may be not so bad, right? Because it's pretty close to the end of my data set. 500,000, way out here, that's going to be a lousy prediction. It's way far past the end of my data set. I would not count on that being too reliable. What do you guys think? Not too bad, right? In general, this chapter should be relatively easy. Let's take a look at some of the in-class examples here for this second set. So this says, I want to pull up this one I have over here. All right. Carrie and Danielle wanted to investigate if tapping on a can of soda would reduce the amount of soda expelled after the can has been shaken. For their experiment, they shook 40 cans of soda and randomly assigned each can to be tapped for either 0 seconds, 4 seconds, 8 seconds, or 12 seconds. Then, after opening the can and cleaning up their mess, the students measured the amount of soda left in each can in milliliters. Below are the data and a scatter plot. So here's our data for, after tapping for 0 seconds, we got a 245 left, 255, 250, 250, etc. Right? Everybody's okay? So those are all so we made our scatter plot. Notice that tapping time is the x-axis, that's in seconds, and the milliliters of soda remaining is the y-axis. And we've drawn in a best fit line here. So who can describe the direction, form, and strength for this scatter plot? Okay, because it's sloping up. Mm-hmm. I would think it's linear. I mean, it looks reasonably linear to me. Quadratic, I'd expect to see like a horseshoe shape, right? So I think linear is fine for this. That's what I would pick. Yeah, moderate to strong, I think, is all appropriate. Okay, everybody feel okay there? Okay. The regression, or the equation for the regression line in the following example is given as yada, yada, yada. Identify the slope and y-intercept and interpret each number in context. So y is the amount of soda remaining, and the x is the tapping time in seconds. So to describe the slope, you'd say for every one, and then you fill in the x value for x. So every 1 second tapping on the soda can, we would predict, and then the slope, 2.63, fill in the unit for y, milliliters of soda remaining in the can. That's it. So for each for 1 second tapping on the can, or each additional second tapping on the can, we'd expect 2.6 whatever an additional 2.63 milliliters of soda remaining in the can. Something like that. Does that feel okay there? I like to start with the X, but
Were we starting with the Y?
it doesn't really matter. I think that if you're trying to get into a sentence, starting with the X kind of makes it a little bit more cause and effecty, right? Because the X is like the independent variable, the Y is the dependent. So it makes it a little bit easier to write the sentence, but it doesn't really matter. How about the y-intercept?
It's at 0, so 2.6.
Mm-hmm. So when what's at 0?
The tap.
Okay, when tapping for 0 seconds, we predict 248.6 milliliters of soda remaining. Does that feel good? Okay. Using the equation above, determine what the predicted amount of soda remaining would be for the indicated tapping times, if applicable. How are we going to do this? What? Just plugging them in, right? Somebody grab a calculator and shout me out some answers. Luca, do the first one. Damien, do the second one. Reese, do the third one. You're welcome. Correct. 261.75. Luca just plugged 5 in for tapping time and pressed enter. Correct.
Still going. Is it 327.5?
You didn't type anything in wrong, but that's not the right answer. What's wrong with it?
What did she say?
She said 325 point something or other. Think about what you're being asked to do here.
Bigger than that. She said 300. Oh, it's extra.
It's extrapolation. Should you use the model to make a prediction? No. So you see how the directions say if applicable? You would say, because this is extrapolation, it's, applying the model here is, incorrect or whatever. You would not want to do that. You got the trick question, Reese. I'm sorry. But you plugged it in correctly. Does that feel okay, guys? Do you think I'll try to pull this trick on you again on the test?
Probably.
Yes. So be careful if you're asking to make predictions that it's actually something you should be making a prediction for. Okay. From the experiment performed, tapping on pop cans, find and interpret the residuals for the indicated cans. Who can find me the residual for when I tapped for 4 seconds, I had 260 remaining? So my residual should be 0.88. The known minus the predicted. I just did it all in one line on my calculator. Why is this thing here now? My computer's being so strange today. When did that move to the middle of the screen? It's been there.
Yeah.
Shows what I've been paying attention
What
to.
did you do to get that 180?
So I did 260, that's the known value,
Yeah.
and then minus when I plugged 4 into the model, that's the predicted value.
Oh, multiplying by 14.
Yep. So I had like that thing. Okay, let's race. Tap for 8 seconds and then 255 remaining. I got negative 14.64. NBD, right?
That's not considered extrapolation. Because you're still within the time.
Right. This is an actual data point.
It's just not realistic that you can't have negative 14.
No, that's the difference between the predicted and the actual. So that's not talking about how much soda is remaining. That's the difference in your prediction from the actual.
Oh, right.
Mm-hmm. Which should go and make sense. I think that's this one right here. I know that's a pretty big residual. So that seems to track with when I look at the graph. All right. We designed a study to investigate the relationship between the row that a student is sitting and their grade on a particular test. We make row number our independent variable with row of 1 indicating the row closest to the front of the classroom. Based on our data, we find the following statistics. Blah, 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 blah. Use the formulas below to find the equation for the linear regression. Interpret the values of the slope and y-intercept in context of the problem. So if I round my answers to 3 sig figs, I'd say y equals negative 1.12x plus 85.7. Everybody feel okay there? No big deal, right? Just plug the stuff into the formulas and that's it. That's all she wrote. So slope is m, y-intercept is b. So I'm just using those two formulas right there. And just plugging the values from up here in. And then I write this with my value for m and b plugged in. No big deal, right? Uh, 10 students in a mathematics course measured their height in inches and weight in pounds to determine if any correlation exists between the two measurements. They make the value of height the independent variable. The table below gives the recorded values. Use your calculator to find the least squares regression line for the data. So let's do that. So I'm going to start just by typing my data into my calculator. I think you guys know where to put that at this point. We've done this a bunch of times, right? So I'd encourage you, again, just following along on your own machine. I think just kind of going through the steps and pushing the buttons and seeing the menus and all that jazz kind of helps me to remember it anyway. I would think it would help you as well. So once I've entered the data in, I'm going to exit out to the main screen. I'll press Stat, go over to Calc, and then pick LinReg. Make sure that my lists are in the right places. And if I'm going to be asked to make predictions, notice that it doesn't ask me to do that. But if it was asking for a prediction, I'd also want to store my equation into Y1. So to do that, I just press the vars button and then go over to Y-vars and then pick function and then pick Y1. I'll just show you that. You don't have to do that, but if you have to plug values into your model later, it's really convenient to just have it stored in your calculator. So there is my slope and my y-intercept and my r value. Notice that in part B it asks us to check to make sure we get the same thing using our formulas and such. My r value is the same, right? Very cool. So far so good. So to check with my formulas, I need to find the means and standard deviations for those two datas. How do I do that? Stat, calc, two variable stats, L1 and L2. Oh, thank you. So now my means and standard deviations and such are stored into my calculator. So I'm going to do vars statistics. And do I get... There's R. Times, and then my sigma y, vars, statistics, and then command 7, and then I need my sigma x, so vars, statistics, command 4. Oh, fiddlesticks. All right, so it didn't remember my R. I'm just going to type it in. I guess I should have stored it somewhere else. Oh. What do you mean, undefined? Ah, that just... Yeah, what happened here? Oh, I see. It didn't overtype there. So there's the slope. That was what we saw before, right? At 7508. I stopped really paying attention after that far, but that's fine. And then we'll do this one. So vars statistics y bar, which is 5, minus my slope, so second negative sign, I'm giving my ands, times var statistics, and then x mean is 2. And negative 330.8, I don't remember the rest of it, but that was the same values before. Everybody's cool?
Same values as when we did the line, right?
Yeah, or thereabouts.
The lines are all set.
Just saying to check. The part B says check the equations for the regression using these formulas. Just demonstrating to that you get the same result. And then it says use your calculator to graph the data as a scatter plot with the regression on the graph as well. So because I stored my regression equation when I wrote it, that's already in my y1, so I don't have to type that in. What I'm going to do is I'm just going to go to stat plot, so press second y equals. I'm going to turn that plot 1 on. I'm going to make sure I have the first option selected, that's the scatter plot. And I need to change my x's to L1s and my y's to L2. And then I'm going to do zoom. Okay, I'm going to exit out of here and then do zoom statistic, which is command 9. When I do that, the calculator automatically adjusts my window so I get a good picture of my data. And because I stored my regression line before when I did that, draws that in there for me nice and neat. What do you guys think?
Is there a way that we can see the one that's the difference between the point and the prediction?
To the residual?
The residual, can we just plug it all and get all over it?
Yeah, how do you do that? Let's see. So if I go to L3 and I do, where is that at? I'll find it in a second. I have to remember where it is. I guess I know what it's called. I could just, oh, I bet it's here. Yeah. So if I go to second list, so I press second and stat, that opens the list command. If I go to names to the bottom, I pick resid. That's short for residuals. And I think I just press enter there. And that should give me my residuals for every...
Where did you go? You went second stat.
Second stat, and then it's at the bottom of the names column. And that, I think, gives you all the residuals without having to do anything. Let's just check that real quick. So negative 17.55 should be 155 minus, and then I have that written down over here, 7.5085. I'm just going to do that much of it times that first x was 67, and then plus negative 330.826. I know there's more decimal, but I'm just going to stop there. So that's negative, that first residual should be negative 17.2-ish. And that's what I'm getting there. So I'm quite confident that that is doing what I think it's doing. That's pretty nice though, right? Alternatively, I think if you did, you could probably do L2 minus vars, y vars, function y1 of L1, and that'll give you the same thing. So it's taking the known y's from L2 and then subtracting from it the predicted values So as long as you stored your regression equation when you made it, you can do that y1 of, and it'll handle that way also. Does that feel good? No big deal? I hoped not. All right. That's it for chapter 14. So the test, you should be able to interpret a regression equation, explain what the slope and y-intercept mean in context. We've practiced that a couple of times now. Know what changes to the data set do and do not affect correlation. Given means and standard deviation for a data set, calculate the equation for the best fit line. We just practiced that a minute ago. You basically just use those two formulas. Use a best fit line to make a prediction. We know how to do that. When don't you do that, though? If you're asking to be extrapolated. Identify the independent, dependent variables for a situation. Use data to make a scatter plot. Use your calculator to find a mean point. Complete a table and use the results to find R, kind of like we did in the activity. Use the calculator to make a line a best fit from a data set. That means just doing the LinReg. Convert raw data into rank order data, and then use that rank order data to do a Spearman coefficient. You guys want to do that again?
Yeah, I was about to ask.
That can be kind of tricky. Yeah. Let's see here. All right. So where's my pen? All right. So let's say we're finding the Spearman for this one. This is just from the in-class examples. Notice this data set here is exactly the same data set we were just working with. Did you guys notice that?
Yeah.
So what I'm going to do is I'm going to just start by ranking the values in the height, or these heights, and I'm going to put that sorted values in L3. So I'm going to go up to the title of L3, and then I'm going to do stat sort descending. Oh, I can't do it in there? All right, whatever. That's unfortunate. All right, so my biggest value is 71. So that's going to be rank 1. My next biggest value is 70. So that's now the third and fourth numbers that I'm ranking. So those get rank 3. Notice we're skipping 2 because we've already ranked 2 numbers here. And then next is 69. I'm going to give that rank 5 because we've already ranked 4 numbers. So this is the 5th number we're ranking. And then I guess let's look here. Are there any other ties? No. Okay. So then we just go 6, 7, 8, 9, 10. And I'll do the same task here for L2.
Does it matter if you sort D or sort A?
Not really. As long as you're doing the same thing each way, I think you get the same value for the Spearman. So 218 is our biggest, and then, this is just driving me nuts. And then 200 is our next one, and then 196, and then 190, and then 88, and then 84, and then 170, and then 55, and then 38 and 136. Stop. So far, so good? Okay. So what I'm going to do now is I'm going to set up my rank order. So there's one little hitch, is that my rank orders for the ties aren't going to just be 1 and 1 and 3 and 3. The reason I can't just do that is because if I add up all the numbers here on this list where I had ties, and I add up all the numbers on this list where I had no ties, I don't get the same total. Right? I'm going to end up being too short here. I'm going to have my number when I add these up is going to be 2 less than this number when I add these up. So instead of giving the yellows rank 1, I'm going to give them the average of first and second. And instead of giving the green ones both rank 3, I'm going to give them the average of places 3 and 4. Is that okay? All right, so now I'm going to go ahead and type this in. So I'll do 7, and then 3.5, and then 1.5, and then 8, and then 1.5, and then 3.5, and then 6, 9, 5, and 10. And I'll do the same thing here. So 8, 2, 1, 6, 3, 5, 7, 10, 4, and then 9. And now I'm just going to run a linreg on L3 and L4. And the R value that spits out of that is going to be my Spearman. So 0.902. Does that feel okay there, Luca?
Yeah.
So the hardest part is just like, the hardest part is just dealing with the ties. So I've just typed in my data, just, like that's an ordered pair, that's an ordered pair.
What is like
So what the Spearman statistic is going to show you is the strength of like a positive, like an increasing or decreasing relationship. It's not going to tell you how linear it is like the PMCC does, but it'll tell you if, is the data generally, like is there like a positive relationship between X's and Y's, even if it's like curved or like, like doing weird stuff, if it's generally getting hot, bigger, generally getting smaller. It'll show us that. Does that feel okay? So instead of telling you how linear the data is, it's telling you how like associated the data is with it as like a, like a positive or negative effect. As the X's get bigger, the Y's also getting bigger, but it's not telling you how that's happening. It's not necessarily saying it's linear, quadratic, or whatever. It's just telling you it is. Does that feel okay? Okay. So for the Sunday's problem set, you guys are going to have 14.3 to go along with the 14.1 and 14.2 that were already assigned that, 3 of you did. The test, I think I've scheduled for Monday. Is that right? Tuesday. That's what I meant. So Friday. How are those of you that have surveys? How many responses do you have on your survey? 3. Okay. Everybody here, get out your tablet, go to the class page here, find the announcement part where I have all the survey links in there, and fill them out. Remember where you left off, you don't get them all done, but every single person in this room needs to complete every single one of those surveys. There's not that many, there's like 13 of them total or something. Many students decided to collect data from an external source, which is great, totally fine, but some of us are still doing surveys, so we do need to help those people out in giving them your data. But it's not so bad. In years past where I've had 60 or 70 people and they're like all basically doing surveys, it's a lot of surveys to fill out.
Where is it?
So if you go to the My Notre Dame page, if you scroll all the way down to where the announcements are, there's one that says surveys or whatever, and it's just a list of the titles and they're just hyperlinks to their Google Forms. If you find something that doesn't work, please let me know, but I think they're all, well, other than the one person who's doesn't have a hyperlink who hasn't given me their survey. If you look at the list, there's one person that doesn't have. Yeah, they just haven't given me their survey. I don't know, they'll get it to me sometime and I'll update it or whatever. But that's why that one doesn't have a hyperlink, is because I don't have a survey for them.
If we did just do outer source,
Mm-hmm.
how do we turn that in?
Just email me your Excel sheet or whatever.
Does that need to be with a special subject?
I'm not too worried about that for this. Yes. Yes. Yeah. I think if you sent me, I think I put in the survey stuff already, right? If you sent me either a survey or your data in an Excel sheet, I should have recorded that already in the IA survey. If you did that, I tried to get that in pretty quick.
Do I send it as a PDF?
You can just send it as an Excel sheet. It doesn't matter, or Google Excel or whatever. You'll want it in an Excel sheet at some point. So if you haven't done that, you certainly want to do that.
Yeah, I could have sent it to you instead of where I found it.
So I want in a file, like an Excel sheet.
Yeah.
Yeah, like a CSV or whatever it is that you download, that's fine. Yeah. Whatever you downloaded it from you found a good source where you're able to get the whole data set just in a file, right? You didn't have to collect, do any data transcription. Some people had a crappy situation where it's like,
No, I had to insert everything.
oh, you had to enter everything in?
Yeah.
That stunk.
Yeah.
Some people found a source where the whole data set was available as a download.
Yeah, mine was too, but I couldn't open it.
Oh.
It wouldn't, when you did it, it worked, but I wouldn't let it open, so I had to go through.
Ugh. You should have gone to IT and been like, hey. Yeah, I would have been like a 20-minute conversation to save an hour of time. It feels like a good trade to me.
Hour.
Okay, hour 2, yeah.